Welcome to the Temperature Sensing and Cooling Footwear Senior Design Project.
Our team consisted of 6 engineers from 4 different disciplines, as well as our guide Jerry Garavuso and our client Dr. Kurt Fleschner. Our project aimed to develop a temperature sensing and cooling footwear system to prevent foot ulcerations often suffered by diabetic neuropathy patients. To achieve this, we focused on the 3 main functions of temperature sensing, cooling, and prevention.
The need for ulcer prevention is significant, as more than 30 million people in the United States have diabetes, and data shows that 85% of diabetes-related amputations are preceded by foot ulcerations. Increased foot temperature is the main contributor to the formation of foot ulcerations. Thus, our design focuses on taking preventative measures and reducing the risk of ulcer formation and requirement for surgical intervention.
Due to the extensive nerve damage, typical regulatory functions of the foot are lost. It has been shown that these people with diabetic neuropathy have a higher average foot temperature than people without. This increased temperature has been correlated to a higher risk and incident rate for ulceration when the foot is above 32 degrees Celsius. Thus, it is necessary to cool the foot and maintain a temperature below 32 degrees Celsius to prevent ulceration. While the entire foot is affected, areas of concern are the ball of the foot, the toes, and the arch.
The 2 main functions of the system are sensing the temperature and cooling the foot. In a typical shoe, the sole is the most insulating feature and has the most potential to improve heat transfer. Thus, we focused our design on the modification of the shoe sole. The design for the cooling function is divided into 2 sub-functions, removing heat from the foot and dissipating it to the environment. As shown on the diagram, the heat is drawn from the foot via a water reservoir located underneath the insole. The reservoir is actively cooled with a thermoelectric cooler, which has a cold side in contact with the water reservoir and a hot side in contact with a heat sink. The heat sink, with an integrated fan, creates airflow through a cross channel to allow heat to be dissipated to the environment, as shown with the arrows at the bottom of the screen. For reference, the thermoelectric cooler, the heat sink, and support cage are located in the modified Hoka shoe sole.
The water reservoir was 3D printed with a flexible outer frame and rigid support arches. A clear polyethylene cover was adhered to the outer frame to see the water flow and to allow easy transfer of heat from the foot to the water. A resealable hole is used to control the amount of water and air in the reservoir to allow for optimal flow and transfer of heat from the front of the foot to the back.
This slide shows how the electrical system is designed. The purpose of this design is to sense temperature and activate the cooling system when the temperature threshold has been exceeded. Power flows from the battery to a switch to power the Arduino. Also, the battery voltage is run to a rail on the through-hole board, where the voltage regulators will step down the voltage to 5 volts and 3.3 volts respectively for the Peltier cell and the fan. The NMOS transistor is used as a switch to power on and off the fan and the Peltier cell.
The Arduino Nano is controlling the temperature sensing system, initiating the cooling components, and recording temperature data into the SD card. A voltage divider between a resistor and a thermistor is going into the Arduino's ADC. The readings are then calibrated to output the temperature to the serial and SD card. Once the temperature surpasses a threshold value, a digital signal is sent to activate the NMOS switches, powering the cooling components.
This is the demo that shows how the temperature sensing activates the cooling system. The Arduino is controlling the NMOS switch, which when activated will run the fan.
So the system is activated to run at temperature greater than 25°C. When heat is applied to the thermistor, the fan should start, and when it cools back down, it turns off.
A primary impact of our system is that it will improve the quality of life for people with diabetic neuropathy by reducing their risk for ulceration and foot problems through maintaining the user's foot below 32 degrees Celsius. This also means reduced strain on the healthcare system, as less neuropathic patients will require additional care. This design provides proof that we can measure foot temperature accurately and cool the foot within a footwear system. With the ultimate goal of this project being a consumer product, this prototype must be redesigned for durability, safety, and marketability, and a case study must be performed to prove its efficacy.
Lastly, our team could not have produced this functional cooling footwear system without the help of subject matter experts, our MSD guide, and our client Dr. Kurt Fleschner. Thank you to everyone who contributed to our project.